In this video, we are going to be learning about the physical properties of alcohols, phenols, and ethers. Before we begin, let's talk about classification of alcohols. Alcohols can be classified by the number of carbons the carbon that the OH group is attached to. So what does that mean? So here's the OH and here's the carbon that OH is on. When we're classifying our alcohols, we look at how many carbons that carbon is attached to. If that carbon is attached to one other carbon, it is a primary. If that carbon is attached to two other carbons, then it is secondary. And if that carbon is attached to three other carbons, then it is a tertiary carbon. So we're always looking to see how many carbons is this carbon that's attached to the OH. What is it attached to? That will come up when we talk about our reactions. Let's classify these alcohols as either primary, secondary, or tertiary. Go ahead and pause the video and unpause the video when you are ready to check your work. Okay, so this carbon here has the OH onto it, and so I see two other carbons attached to it, and so that is secondary. This OH is attached to that carbon. This carbon is attached to that carbon, and that carbon, and so this one is tertiary. Let's think about the geometry of our alcohols. How many electron groups are around the oxygen atom here? There are 1, 2, 3, 4 electron groups. That's going to help us decide what the geometry is around our oxygen. The shape name for 4 electron groups is a tetrahedral geometry. The molecular geometry, since lone pairs are not really visible, is this molecule is really bent in shape. That means that even though we draw it linear like this, in real life it is bent. Much like water is bent. Why did I draw another OH? Water is bent and alcohols are bent. And so this bond angle is not 90 or 180, that's 109.5 degrees, which was the last question. Let's think about the different intermolecular forces before we go on to the next slide. So since this molecule is bent, we do have a permanent polar dipole happening. It is bent. We have a polar covalent bond between the carbon and the hydrogen, and the hydrogen and the oxygen, those are the dipole moments. Oxygen pulling those electrons away, trying to hog them all. So this part of the molecule is polar. Since it's polar, that means that we can have dipole-dipole forces. All molecules have dispersion. Since it's polar, it will have dipole-dipole. And since, let's see, what types of intermolecular forces are possible? This molecule could serve as a donor for hydrogen bonds, meaning that it has a hydrogen attached to the oxygen. And this molecule could serve as a donor or an acceptor. I've already written donor. This molecule could serve as an acceptor, which means that there is a lone pair on the oxygen. that can accept a hydrogen bond. So between different molecules, of alcohols, we could have hydrogen bonding, dipole-dipole, and dispersion forces. So alcohols and phenols, they can serve as donors and acceptors for hydrogen bonds. So you can see that this molecule here is serving as a donor, and this molecule here is serving as an acceptor. So we can have hydrogen bonding between similar shaped alcohols and phenols, because phenols also have an OH group on them. Ethers have the same geometry, so the ethers are bent also. So there is a dipole moment, but there's no H off of the O. So for hydrogen bonding, ethers cannot donate a hydrogen for hydrogen bonding. So between two ether molecules, there will not be any hydrogen bonding. There will be dipole-dipole forces and dispersion, but between two ethers, there will not be any hydrogen bonding. So that is a difference between ethers and alcohols. Thiols do not even have an oxygen. So even though ethers can accept a hydrogen bond, thiols cannot accept and thiols cannot donate for hydrogen bonding. When we talk about solubility, we have to think about what types of intermolecular forces these molecules can form with water. Since water can serve as a donor, then even though ethers cannot hydrogen bond to themselves, ethers can hydrogen bond to water because they can serve as an acceptor. Alcohols are more soluble than ethers because they can both donate and accept hydrogen bonds. So they are both acceptors and donors for hydrogen bonds. You can see this one is a donor, and then the water is accepting. And then in this hydrogen bond over here, the water is the one donating, and then the alcohol is the one accepting. And then the dotted line here represents the hydrogen bond in between the two. There are limitations though, and that has to do with how long the carbon chain is. The longer the carbon chain, the less soluble it is. That's because the carbon chain part of the molecule is nonpolar. And so this part is only dispersion forces. And so once this gets big enough, it's going to essentially block any hydrogen bonds from forming, because this part is so big compared to this tiny little head on the molecule. So as the carbon chain gets bigger, you expect this to become less soluble. Generally speaking, 4 carbons or less is soluble, but we want to rank molecules by their solubility. So it's important to recognize this relationship between the carbon chain length and solubility. So that diagram underneath all the scribbles helps to depict how that carbon chain length matters. As we expand the carbon chain, this nonpolar part of the molecule becomes so big that it will essentially block the hydrogen bonds from forming. So let's make a prediction. Which of the following compounds would be most soluble in water? Go ahead and pause the video and then unpause the video when you're ready to check your work. Okay, so we have this one down here, which is an alcohol. Both of these are alcohols. So the alcohols are more soluble than ethers. The ethers are dipole-dipole, but ethers more soluble than alkane. And so this one's worse. This one's alkane. And so that one's going to be the least soluble. So if we number this one number 1 for being the most soluble, this one would be a number 4 for being the worst. This one has more carbons than that, and so that's going to make it less soluble. And that's because this part of the molecule is nonpolar. Evaluating whether B or D is next in the ranking is kind of difficult because this one does still have some hydrogen bonding possible, and this one is dipole-dipole, but less carbons. And so I can't really have you evaluate whether this one is higher than that one because there's trade-offs there. When we evaluate the melting point and boiling point of a substance, we are thinking about intermolecular forces between similar molecules of a pure compound. So all of the molecules have the same composition. So we're trying to think about what intermolecular forces are possible between a molecule and a molecule that looks just like it. We have to think about things like the shape of the molecule, because much like before, if our molecule is straight versus branched, the branched, you might recall, has fewer dispersion forces. And so that's going to influence our melting point and boiling point. So branched is generally lower melting point, boiling point compared to straight. And so we have to think about all these different intermolecular forces, because the stronger the intermolecular forces, the higher the melting point and higher the boiling point. So as we increase the chain length here, you can tell that the boiling point increases. Straight chain alcohols with less than 12 carbons are generally liquids at room temperature. You can think of alcoholic beverages, you can think of rubbing alcohol. All of those are liquids at room temperature. So just like water is a liquid at room temperature. That's unlike our hydrocarbons, which were often gases at room temperature. These have a higher boiling point, and so room temperature is not warm enough to have these boiled yet. They are liquids at room temperature. Let's do a practice problem. Which one of these molecules will have the highest boiling point and why? Once you have a reason, then go ahead and unpause the video. So this one will have the highest boiling point. And so my claim is that it will be this one. My evidence will be it's an alcohol. I'm not making complete sentences. This one is an ether, and this one is an alkane. So my claim is that this one's going to be the highest because it's an alcohol. Now for my reasoning, I have to explain that alcohols are better, have higher boiling points than ethers or alkanes. I can't just say that they have higher boiling points than ethers or alkanes. I have to say why. So they can form hydrogen bonds. Unlike ethers or alkanes. Hydrogen bonds are strongest intermolecular force, increasing boiling point. Phenols are slightly acidic, and so when you go into lab and measure pH of alcohol solutions, alcohols are fairly similar to water in pH, so alcohols should be neutral. But phenols are slightly acidic. So acids have protons that come off in solution. So this hydrogen here can come off in solution. That's because these aromatic ring here can help stabilize the negative charge on this oxygen. So the negative charge here can actually enter into the ring and stabilize this conjugate base form of the molecule. So this one is slightly stable, so it's okay letting go, unlike alcohols, regular alcohols.